Okay. All right. Can you hear my voice now?
Yes, sir.
All right. Let's start again. Let's go back to the last problem that we had. All right. Since we have this one here, you see this is a square plus a square, but then it's negative one. So this is what we call squared plus y squared, but this is equals negative one. So this is impossible because these squares. This only possible. That's even impossible. No solutions. Yeah. Therefore, this is uh, neither parabola, hyperbola, ellipse. This is empty set actually. Okay, uh, so neither parabola, hyperbola, nor ellipse. Okay. In fact, if you this one, wait, I haven't the screen yet. Okay, share the screen. Oh, okay, sorry. All right, if you look at this equation here, the last one we had, this is a square plus a square, then equals negative one. Okay, but so this is impossible. So no solution from this one. So it is neither parabola or hyperbola nor ellipse. In fact, if you try to plot this one, this is empty set. Okay, so it's neither. So that's the for this one. All right, so let's try another one. For example, 12. So 4x squared minus 4y squared. Let's see. Just write this quickly. 4x squared. 8x plus y plus 6. Okay, that is 12. Y squared plus 8x plus 12y minus 6 equals 0. All right. So let's pair this 4x squared with 8x, uh, 4y squared with this one. So you get, take the x out, and then take also, well, because it's negative, so you take this one. And then this become minus. Then this is 3. Correct. Okay, 4. And then you should subtract what is square root of 1 there. Then you get to have y minus 3 halves and subtract 9/4 minus 6. Or just move this 6 to the right hand side. 6. Okay, so then you have to remove this 4. So it becomes x plus 1. Um, 6. And then you so become plus 4. And then here we got plus 9. Here you have 19. All right, so then you have, and then subtract 19. You get 1 there. And here you have um, 19, so x plus 1 squared of 19 over 4 there. Then over square root of also 19 over 4. This one. Okay. So you have a, you can recognize this one. Square minus square. This is hyperbola. Okay. Hyperbola with this a, this is A, this is B. Okay, so the asymptote is y equals B over A. Sorry. It should be plus minus B over A x. Because A and B are the same, so you get okay. So you get this picture here. So this is the asymptote. So you have, let's see, no y. You get this one here. Okay, so this is the picture. All right, questions? And probably the last one here is, sorry, that's like problem 13, for example. 4x squared minus 24x. So one peculiar thing about 13 is that you have no y's here. So what is it? For x squared 24x plus 36 equals 0. Okay, so let's take the 4 out. So this x squared minus 6x plus plus 6. Then so you can cancel the 4, doesn't matter. And here you have let's see, this is x minus 3 there, and minus 9 plus 6 plus 0. So take the 4 out, doesn't matter. Equals, this is minus 3. All right. Okay. So then you have x equals, let's see, square root of 3 plus minus square root of 3 plus 3. Okay. So this is a point. This is 2 points actually. This is not a not even a parabola. Okay. So I just say just points. Yes, 2 points. So this is neither parabola, ellipse, or hyperbola. Okay. So if we have this, this is various kind of quadratic equations in two variables. Okay, quadratic equation in two variables. So some of these are ellipse, some might be ellipse, hyperbola or parabola. Some are maybe not. Some maybe just has no solutions at all, or just points like this one. Only points. Okay. So basically, this is from the section 11.1, 11.2. This is what you need. Okay. All right. And let's see what else. Okay, so let's move to, we postpone the, we talk about the translations, but we'll postpone this rotation of axis later. This rotation of axis will responsible for the, this term here, what's there? It's the product of x and y, so xy term. So problem 1 to 16 that we attempted no xy terms. Okay, xy terms. So the xy terms means you have rotations, but we'll see that later on. Okay, at least we don't need this. We only use the translations. Okay. All right. Let's continue with the, sorry, this is the 10.4 parametric representation of curves and plane. All right. Now if we try to represent a curve by a graph of functions, it is very limited. Okay. Um, um, represented by functions. It's very limited. What do I mean by graph of functions? This one. But even some simple curves cannot be represented as functions. There. This is not the functions. Graph of functions because, well, you have vertical line tests. Vertical line. If you recall what you have in first semester, if a graph is cut by vertical lines, then at most you have one cut only, one intersections. If you cut it here, then you don't have any intersections. If you cut it here, you have two. Cut here, you get one. Right? But so this is not a function. Okay, so some simple things cannot be functions. Other things This simple thing is not a functions. So many things we cannot, so we try to find some way to represent a curve, okay? And this is represented by something, think the curve as a path of a particle. Path of a moving. So if a moving particle, then there, for example, going these directions. You start here, at some time you end up with here, t equals b here, and t equals c, and we end up. This is the initial point. This is the end point. Okay. And the other thing is, well, you describe every time as, so the curve, say this is curve gamma. Gamma is described by its position in xy coordinate. Using time t as parameter, or say variable. Parameter and variables are, well, pretty much the same. So here x is something equals, and y is something. For t from, say, from 0 to c, something. So this is what we call parametric representation of a curve. Okay. Representations of a curve. Okay. Here. So x is defined by a function f of t. Y is described as g of t in some intervals. Okay. All right. For example, let's do some example. Okay, that's a curve. Is defined as, let's see, x is, say, just cosine t, and y is just sine of t, and t start from 0 until, say, pi. So what do you get here? So what is the curve? Let's see what we get here. All right, what we know about cosine and sine, how do they relate? Well, since we know there's cosine squared t plus sine squared t equals 1, but this means cosine t is the x. So this is a square of x. And this is a square of y. What? But this is a circle of, say, not unit circle. Radius 1. Okay. So this is a curve. This curve, circle. But is it really the circle, radius 1? Let's see. All right. It starts at time 0. At time 0, the initial is, let's see, if you plug in t equals 0, you get this as 1, y is 0. There. Yeah. And when t equals, say, pi over 2, 90 degrees, so you have cosine is 0 and sine is 1. So then let's go. So it seems like you're going this way. So the endpoints, t equals pi. So you get, let's see, pi cosine is -1, y is 0. So you end up here. Okay. So this is not really a circle, but just the half circle, semicircle there. So we can now answer this questions here. What is the curve? This is the upper semicircle of radius 1. Okay. Questions? This is one way to describe this one. All right. Okay, and two. So follow this one here. Same question again. What is the curve defined by t square? Y t is just t. T from 1 to say 4. Okay, let's see. So we what we're trying to do here is find some relation between x and y. As we have here, we find a relation between x and y. So here between cosine and sine. But something that easy would be something like this one here. Pythagorean relation here. So cosine squared plus sine squared equals 1. All right. So what we have here. So let's see. If y equals t, then this should be from this one. So what we get here is that x equals, so then this is parabola. Okay, so the question is, this parabola this way. Okay, so now the question is about, is that the whole thing? No, because this is only a part of this one. So for the initial, t equals 1, then you just plugged into 1 to here. So you get the point 1 becomes 2, or 1, 2, 1, 2, 2, is 1, 2. And when, say, t equals 2, for example. See the direction. When you plug in 2, you get 2 here, 2, 4, 8. So 8, 2 here. And t equals 4 is 4, 4 squared 16, 32. 32, 4, 4. Okay, so it turns out that the curve is this one here, going that direction. So this is the curve. So this is not the whole parabola, but it's only part of this parabola. Okay. All right, so let me introduce another thing. Okay. So a curve is called simple if, let's see, okay, here. A closed circle, closed curve means that you have no the initial and the endpoints are just the same here. This is closed. Okay, closed. Simple means doesn't have any self intersections. This is self intersection, so this is not simple. This is self intersections, no, not simple. Okay, closed meaning that you have a. This is not closed because the endpoints and the initial points not the same. Okay, so that's classifications of curves. What you call simple, the initial point, is the endpoint. So this is the example circle, and uh, what we call curves here is always oriented. So it has a orientation. So you have a directions or directional curves. Not sorry, oriented, directional. So it has the this arrow sign here. Okay, so initial endpoints, and this is simple also. Sorry, initial equals to, okay, this is a simple. This is a closed curve also. Sorry, this is closed, closed, closed curve. Initial equals n. And the other thing is simple. Simple curves, meaning no self-intersection. No self-intersections meaning, well, the easiest would be this one here. This is not simple. Sorry, I should say this one. Still going there, going there, going there. no self-intersection. So this is simple. Here you have self-intersections. Not simple. Okay, so based on this, we can go back to this picture. So this is not a closed one because endpoints and the initial points not the same, but you have self-intersections. So this is not simple. All right. So this one is not a closed because you don't have the endpoints and the initial points not the same. And then, but this is simple, no self-intersection. Here we have a closed one, but you have self-intersections. So this not simple. This one is simple and close. Okay. All right. So let's go on with the again recognizing the curve. So graphing the curve. For example, this one here. Um, eliminate the parameter here. So here x is given by t squared plus 2t. Y is given by t minus 3. T between negative 2 and 3. Okay. So the question is, well, try to recognize what kind of curve is this and sketch. Okay. So here we try to find some relation between x and y. Okay. Here. All right. We solve this for t. T to y plus 3 and substitute this t to the x. So you get these equations. Right? Then this is a parabola. You see? Parabola with this vertex. Forget to mention this is vertex of parabola. Opening to the right. So the shape here. And then like this one here. This is the initial point. This is the end point. Okay. And in between you have this point, plot this one. So you end up with this picture. You start with 0, negative 5. So you start here, actually. So that directions. Okay. Another thing is number 2. X is a cos t. Y is b sine t. T is between 0 and 2 pi. Okay. All right. So if we divide this by a, so you have cosine t. You have the divide by b. You have sine t. And again, you have cosine square plus sine square is 1. So you have this one. It's an ellipse with major, minor axis. This is A and B. Okay. And if you plugged in the point, the initial and end points, you have a curve, closed curve, moving from this point, going this way. So counterclockwise. Going uh, one circle, one cycle. Okay. Okay, so the question is, so if you have this one here, Curve 1, first curve defined by this. Well, we've done this one. T is between 0 and 2 pi. And compare this to curve 2. T again is 2 pi. So what's the difference? Because from 1, you get x squared plus y squared equals 1. Right? Okay. Just step by step. Cosine squared t squared t equals 1. Okay. So you get the picture going. Okay. Same thing, same. But if you plug into 2, well, y squared 2t plus sine square 2t. This is also 1. So exactly the same picture. Going there, also going this direction. Same picture. So what's the difference? So think t as time. Do you recognize any difference between 1 and 2? So always think this is a motion of a particle. So let's see, the first one, the initial point is this one here. Okay, so t equals pi over 2 gets to here. Uh, t is equals to pi gets to this one. Okay, gets to this one here. So moving there one time. Okay. All right. So what about this one here? If you look at the term initial and terminal point, the end point, you get always the same thing here. Yeah. So what's the difference? Do you see any difference between 1 and 2? The motion now. Think of the motion. Hello? Hello? Is there anyone there?
Yes, sir.
What's the difference? Do you see any difference? The picture is exactly the same. You have a same initial point, you have same endpoints, you have same direction. Are these the same motions? Okay, try to plug in t equals pi for these two motions. The first one, where did you get? What point you get?
Plug in how much? 3 pi.
Just pi. T equals pi. Just pi. T equals pi. The first one. What point you get? What's your positions according to curve 1 when t equals 1? What, what point you get there? What is your positions? And here, what's your positions?
One is pi and the other one is 2 pi, sir.
What's 2 pi? As for t equals pi, what is your position here according to this one? What is x? What is y?
Is it 1 and 0, sir?
1, 0. Nope. Is that really 1, 0?
1 0, sir.
Uh, cosine pi, what is cosine pi? There. It's not the initials, this is the middle point actually. Mid, say mid time during between 0 and 2 pi.
Is it negative 1 0?
Yes, 1, 0. So where are you located here? There.
Yeah, there.
But in this one, what do you get here? What's your position here? When you plug in pi here, what you get? Plug in pi, what you get here?
It's 1 0.
1 and 0, sir.
0. Again, you here. And if you plugged in, for example, t equals pi over 2, for example, you get here 0, 1. But here you get pi over 2, pi is negative 1, 0 here. Meaning here. So what's the difference? Do you see the difference? I mean, I have to say, do you sense the difference? You start the same point as this one. But here, when t equals pi over 2, you get to this point. While the second one, you get to this point. So when t equals 2 pi, here you get 1 lap. Think about a motorbike, MotoGP or something. So just 1 lap here. But here, when t equals pi, so just half time, you're already making one lap already. When 2 equals 2 pi, so you're making 2 laps already. Here's only 1 lap. So what's the difference? So you have exactly the same route, same curves, same endpoints, same initial and terminal points. So what's the difference? Can you describe what's the difference between 1 and 2?
Is it like something like double the movement or like opposite sides?
How you call it if you ride a bike? Ride a
Faster?
motorbike. What?
Faster? Is it faster, sir?
Yeah, it is faster. So this is difference in speed. Okay. So with the introduction of a parameter t, you have sense of speed. So here you're making 2 laps already. Here you only have 1 lap. So this is faster because you have a sense of speed. Okay. So here you have, so this is the final thing. If you have think about x squared plus y squared. This is just a circle of radius 1. But that's it. But if you write this down as cosine t sine of t, so this is x with this, with parameter t, you have more information. What is more information? You have directions and you have speed. Okay, so as I say, always say that information is expensive. Okay, so with this, I want additional informations. You have parameter t, you have informations. So with this additional information t, you have more things to get. You have direction, you have speed. Here, no speed, no directions. No directions. All right, so this is the benefit of introducing parameter t to your equations. Okay, so I will end this session here. So let's continue this tomorrow. We'll finish it with vectors also. All right, so let's stop the share, stop record.